Question 9. A mass m kilograms is released from point A down a smooth inclined plane, and once it reaches point B, it completes a circular motion via the smooth circular track B to C to D, and then back through B, which is connected to the end of the incline and has a radius of AM. And we see here that the height here is equal to 4A. Determine the normal reaction of the track on the mass. And we're doing it at B, C, and D, C, and B. Now, just to make one thing clear, at this point over here, this ball at this point over here has got energy, and that energy EP is equal to mgh. Now, when it comes to B, all that energy will be changed into kinetic energy. So at B, the EK is equal to mgh. Now, the h here is 4a, so I can say that it's going to be 4 mga. And so this kinetic energy here will be 4 mga also. Now, at point C, we can see that it has, at point C, and maybe just let me write this over here, at point C, it's going to have two types of energy. It will have your potential energy, and that will equal just mga because it's at a height of A, and the rest of the energy will be in kinetic energy, which will be equal to 3 mga. And at D, it will have potential energy of 2 mga because now it's 2a above the surface, and your kinetic energy will also equal to 2 mga. So in each case here, we can see that the potential energy has been converted into kinetic energy. Now, to work out your normal reaction, you need to look at your velocity, because we are looking at the change in velocity or the change in direction, which gives you your centripetal force. Now, remember our formula for this force is equal to mv squared over r. Now, I'm actually not going to do it in this order. I'm going to start with B, then do C, and then do D in reverse order here. So at B, looking at B, we know that there needs to be a resultant force on it here of mv squared over r. But there is a force down here of mg. So the actual resultant force that's up here will be this mv squared over r and also an mg component. So the reaction force, this reaction force that we are looking at is actually going to be, for B, is going to be mv squared over r plus mg. Now, what is V going to be? Now, we know at point B, we have got this, that mgh ek is equal to mgh, which is equal to that. So we have 4 mga is equal to the formula for kinetic energy as a half mv squared. So I can cancel out my m. I can multiply through by 2. So I'm going to get 8ga is equal to v squared. So I can put this into this formula. I'm going to get m, but instead of writing v squared, I'm going to write 8ga. But what is my radius? What is my r? Well, it's a plus mg, and so my a's are going to cancel. I'm going to have 8 mg plus mg. We're going to have 9 mg. So at B, your force reaction is going to equal 9 mg, or 9 times the force of gravity. Now, let's do the others. I'm just going to erase this, and we're going to look at it for C and D. So I just want to erase a few things here, like that. So looking at C, actually, let me just erase this also here. Looking at C. Now at C, you're over there. We know that you have got your force is down there like that. Now that has been compensated. The reaction force actually is going to be in there, that way over there. So this force inwards is not going to be involved with your mg. So this force inwards is purely going to be your mv squared over r force. And that's going to be your force of reaction. So that's caused by the circular track pushing on that ball. So we're going to get our force reaction is equal to mv squared over r. But what is our v squared at C? Now we know again, at C, we had our EK is equal to 3 mGa. So we've got 3 mGa is equal to the formula for kinetic energy is that. So it's going to be 6 mGa is equal to mv squared. We cancel our m's and we get v squared is equal to 6Ga. I put it into my formula here. So we're going to get m 6Ga divided by your r, and you know that the r is a, so it's divided by a, so that cancels and you get 6 mg. So at C, you're going to get your force reaction is equal to 6 mg. Now finally, in looking at the situation at D, at D, what happens is that you've got your force there. You've already got an mg, and that's actually going to contribute towards the mv squared over r force, the centripetal force. So the reaction force, the force reaction, is going to equal mv squared over r, but part of that will actually be provided by your mg. So you're actually going to subtract the mg there. So now putting this into using my formula over here, we know that D is equal to your EK is equal to 2 mGa. So you've got your 2 mGa, and that's equal to a half mv squared. We've done this a few times now, so that's 4. The m's cancel, and we're going to get 4 Ga. I put that into here, so I'm going to get m times 4 Ga all over a, because the r is equal to a, so that cancels, minus mg. So it's actually going to equal 3 mg will be your value for that. So this one over here is going to equal 3 mg will be the reaction force for that. Now you can feel this for yourself. If you swing a bucket around and you try to keep it at a constant velocity, at the bottom point where the bucket, if you're swinging a bucket around like that, you'll feel in your arm a much more tension than you will at that point over there. It feels easier there, but then it drops around at this point. It's the same when you're on a roller coaster. This is a roller coaster and you were coming down. When you over here, you really get pushed down into your seat, and when you come over here, you actually feel like you're falling out. So we have that situation. At the bottom, you're getting the reaction force, the seat pushing up on you is much greater than at D, and you'd feel that way.